Now that we know some basic Laplace transforms, let's see what the Laplace transform does to a differential equation. So here's a differential equation: y double prime plus 3y prime plus 2y equals 1. And since the Laplace transform is sort of a function that turns one function into another function, we can hit both sides of this equation with the Laplace transform like this. And on the right-hand side, we get the Laplace transform of 1, which is fine. We know what that one is. On the left-hand side, we're taking the Laplace transform of a sum. And since the Laplace transform is linear, we can distribute the transform and also move constant multiples outside the Laplace transform. So we get Laplace transform of y double prime plus 3 times Laplace transform of y prime plus 2 times the Laplace transform of y. Excuse my especially bad handwriting on this one. And at this point, it seems like the Laplace transform isn't really helping because there are 3 unknown functions here: the Laplace transform of y, the Laplace transform of y prime, and the Laplace transform of y double prime. But y prime and y double prime, they aren't completely independent. They're related because they're derivatives of each other. So there must be some relationship, some corresponding relationship between their Laplace transforms. So I guess to make progress on this idea, to see if the Laplace transform really is useful for working with differential equations, we need to know what the Laplace transform does to the derivative of a function, right? What is the relationship between these Laplace transforms? So to work that out, let's find the Laplace transform of the derivative of a function. We're going to have to just use the definition of the Laplace transform because that's all we have when we don't have a nice handy rule for a Laplace transform. We just have to use the definition. So Laplace transform of df dt is the integral from 0 to infinity of e to the minus st times, I'm going to write this f prime of t dt. So that's the definition. And right, the problem here, the issue is that this prime here, this derivative, is causing us trouble. So we would rather not have a derivative on this factor in our integrand. But there's a handy way to move a derivative off of a factor in your integrand, and that's use integration by parts. So we're going to use integration by parts with f prime dt. This is going to be playing the role of dv, and e to the minus st, that's going to be playing the role of u. And when we do our derivatives and integrals for integration by parts, these are going to be with respect to t. Remember, as far as this integral is concerned, s acts like a constant. So when we do integration by parts, right, we have to integrate dv. So the integral of that is just f. So we get e to the minus st f of t from 0 to infinity. And as usual, remember, this infinity is really a limit as the top bound goes to infinity. Minus the integral from 0 to infinity of, now integrate the, or differentiate the u part, so minus s e to the minus st f of t dt. So these minus signs cancel. On this first part here, the top bound, as t goes to infinity in this, what happens to the exponential, as usual, depends on s. So s is going to have to be positive for the limit at plus infinity to make sense. And also for this limit not to blow up, as usual, we have to know that we have to know that f is of exponential order. So f has to be of exponential order, which is not usually a big an onerous requirement because first of all, most functions that we're going to be taking the Laplace transform of in applications, for example, they all are of exponential order. Frequently, they're bounded or polynomial. All of those kinds of functions are of exponential order. So this is a pretty modest requirement here. But if we do require that f be of exponential order, then when we take the limit at infinity, we get a 0 minus, and then plug in 0, and so e to the minus st, when t is 0, the exponential part is 1, and so we just get f of t, or I'm sorry, f of 0, plus, and now we need to do this integral. Well, you know, s acts like a constant as far as this integral is concerned, so we can move that outside of the integral. So s times the integral from 0 to infinity of e to the minus st f of t dt. And what we get here is that, right, this first piece here, this is just s times the Laplace transform of f, and then minus f of 0. So this is the Laplace transform of the derivative of a function. It turns out that the Laplace transform sort of turns a derivative into multiplication by s. Kind of, you know, there's this detail in that there's this other term that shows up involving an initial condition, which is interesting that initial conditions show up. But sort of the big picture version of this is that the Laplace transform turns differentiation into multiplication by s. So that's a first derivative. To use the Laplace transform for second order equations, we're going to need to know about second derivatives as well. So let's work out the second derivative. So again, we're going to have to use a, well, I guess we could actually, we can write this as the derivative with respect to t of f prime. Okay, now we know what Laplace transform does to a derivative with respect to t. It makes it multiplication by s. So multiplication by s times the Laplace transform of f prime minus the initial value of this function right here. And the initial value of f prime is f prime of 0. Okay, but now we have to work out the Laplace transform of f prime, but that's the one we just worked out. So the Laplace transform of f prime is s times the Laplace transform of f minus the initial value of f, so f of 0. Okay, and then at the end, minus f prime of 0. Okay, so putting this all together, we get s squared times the Laplace transform of f minus s times f of 0 minus f prime of 0. Okay, so it looks like, you know, if we needed a third derivative, we could do this whole game again, and a fourth and a fifth. But it looks like the pattern that's forming here is you start with whatever order you have on your derivative. You start with that power of s times the Laplace transform of your function, and then a bunch of initial values. And the initial values, first of all, the power on s decreases each time. So we started with s squared, so then we get s to the first and then s to the 0 right here. And the number of derivatives increases. So for this pattern to really work, you kind of have to treat the Laplace transform as the negative first derivative, which it isn't really, but you know, it makes the pattern work anyway. So then that means in the next term along, we get the 0th derivative of f, which is indeed what f is, and then the first derivative of f. So again, you start with the Laplace transform and the nth power of s. Well, why don't we look at the full formula here? For the nth order, for the Laplace transform of the nth order derivative, right, you start with s to the n times the Laplace transform of f, and then each step along, the power on s goes down by 1, and the number of derivatives goes up by 1. So we go from n to n minus 1 for the power of s, and from the negative first derivative to the the 0th derivative. And then for the next term, we go from n minus 1, s to the n minus 1, to s to the n minus 2. And the function, the initial value, goes from the 0th derivative to the first derivative, and so on. You keep going until, oh, I've made a mistake here, until you run out of powers of s. This last one should be s to the 0th power, so really that's just 1. So this s shouldn't be here at all. Okay, so that is a general formula for a Laplace transform of a derivative of any order. So now that we know how to handle derivatives, or now that we know how to turn Laplace transforms of derivatives into Laplace transforms of the original function, let's have a look at, in the next video, we'll have a look at our original differential equation again.